Okay, this is the promised video on the math-related problems. But before I begin this, I will tell you that none of the problems that I will give you in the exams will have anything more than addition, subtraction, multiplication, and division. Straightforward, everything from the reading materials. Will be a bit tricky, but it will have only simple operations, okay? Okay, this was a question a lot of you actually solved in the assignment area. And you can stick to your own formula if you derive it. Look, if I give you all the data, you can as well as derive the formula during the exams. It's as simple and as straightforward as this. So the question was, UK has a population density of this. Imagine wind power generates this much of watts per meter square, and assume this conversion factor that I will give you. If you cover 10% of UK with the windmill, then what would be the power generated by our windmills in terms of kilowatt hour per person per day? This is the unit that I will always ask for because this is the most straightforward unit for you to make sense with. So the formula is quite simple. If you have to calculate the power per person, it's just the power per unit area times the area per person. So I gave you all these things and you have to just cancel each other out. And I gave you the population density just by taking the reciprocal, and by converting kilometer square to meter square, you can come to this square meters per person, right? And just plug this value inside the formula, you are done. Take this, and then for the power per person calculation, I gave you the value, the wind power per unit area, and you just calculated area per person. So you will end up with watt per person, okay? And I also gave you the conversion factor from watt to kilowatt hour per person per day. So you could just take this value, convert it into kilowatt hour per person per day. As simple as that. Now what I ask you is, that's just if you decide to cover the entire of UK, right? So I asked you only to cover 10% of UK with windmills. Then you'll know that 10% of it is 20 kilowatt hour per person per day. Okay, but that's just the mathematical formula and how to derive these things. The idea in the exams would be you have to make some sort of rational choices given these numbers. Okay, this too you already did in the exercises. If you have questions of answering the rational choices, go to the exercises that people actually did, and then you'll find how they try to reason in those exercises. And this is a question about the evapotranspiration. Again, I really would request you to read the reading material in module 1. I gave you the page number as well. It's page number 79 and 80, and it is a very straightforward problem. So we talked about footprints, environmental footprints, water footprints, and one of the water footprint area, the idea is to calculate how much of green water is available, okay? And the green water availability is a straightforward thing. You have to take the total evapotranspiration of the catchment, but that's not completely available as green water, right? So you have certain amount going towards the conservation of biodiversity. Let's say 30% of area that you can't touch, and something is going towards those 30% of area. So the green water requirement for those biodiversity preservation is, imagine, 150. And during winter and in other times, there will be, of course, unproductive evapotranspiration that you can't call as green water available. So you have to take that away. If you take from total evapotranspiration these two things away, that's just the green water available. Okay, very straightforward. Again, please read the reading material because it has one or two additional steps of complexity, but the idea is quite simple. Doubling time, and this is an exercise also sum of u solved, okay? And the idea is to know from the exponential growth, if you imagine exponential growth, and I'll give you the type of growth in exams if I choose to ask. And the formula for exponential growth is this. And this too, some of you found from the internet and solve the exercise in the assignment section. Okay, so take the first question. The production of carbon fiber for structural use is growing exponentially at 10% per year. If the production volume in 2010 is this much, what would be in 2020? This is just a question that should make you curious. So something is being produced at this point of time in X amount. And if it's going to grow, let's say 10–20% per year, how much of those produced material would be there in, let's say, 10 years later on, 20 years later on, and so forth. Okay. And again, it's just a plug and play in this formula. You know the P naught, because that's the thing that we are starting up with. And you know the T minus T naught, it's basically 10 years, 2020 minus 2010. And of course, please make sure don't plug in 10% because it's a rate, so it's 0.1, and you'll get the P. You'll get how much of metric tons will be there in 2020 here, right? And you can do the same for anything else here. If I give you all the other variables and then ask you to find the rate of growth, it's also solvable. Again, check this example. One special case is that of the doubling time when P over P naught is 2. When I ask you to calculate the doubling time, you can have a simplified formula that's mentioned here. So you can use this to, especially if I ask you questions about doubling time. Okay, but again, this is simple plug and play, and you could see from this equations. Embodied energy problem. This none of you actually even attempted. It makes me a bit sad, but that's where we are. So again, the idea that I gave this exercise to you is that, look, a metal exists in a form of a ore in ground, right? Let's say here the example is copper. The oxide is copper oxide. Theoretically, let's calculate how much of energy is needed if we have to take out copper from copper oxide. That is the ideal energy that's given here. Let's first calculate that. And then if I give you an embodied energy value, that is what is happening in reality, and that's this much, what is the difference? And if indeed there is a lot of difference, why do you think such difference exists? That is all there is to this problem. That is all there is to thinking about this. Okay. So let's say copper can be extracted from natural copper oxide, CuO. The free energy of formation, which is an inherent thermodynamic value, is 127 kilojoule per mole. And this is the amount of energy that must be provided to create 1 mole of copper from copper oxide. So the theoretical one. Okay. How does this compare with the reported embodied energy of copper, 71 megajoule per kilogram? That is the reality. Okay. The calculation of ideal energy per kilogram to reduce copper oxide to copper is basically taking the energy and then dividing it by the atomic weight of copper and then applying a conversion factor so that you know in terms of kilogram, because this is given in moles and all you have to get is kilojoule per kilogram. Okay, convert that into megajoules per kilogram, you get 2 megajoules per kilogram. But the real embodied energy is 71 megajoule per kilogram, and as you could see, the difference is enormous. Such kind of differences exist, and it arises out from the fact that you have to have so many additional steps to actually go from CuO in the ore, in the ground, to really producing copper, the metal. Okay, You have to go towards beneficiation, concentration, all these things that I actually explained in the lecture. And that is why you have to supply such enormous energy. Okay, that's just the idea behind embodied energy. If you solve this problem, you would have immediately seen what's happening. The other numerical problem that I might ask in the exams is regarding the waste hierarchy index. Pause this video and then just go back to the lecture in policy and legislation module, the first one, and then actually listen to the lecture and read the article that I posted. You don't need to read it in full. In fact, you don't even need to read the article. If you listen to the lecture, you should be able to get what I might ask in the exams. Again, it's a very straightforward problem, and you would immediately understand how to solve this with the formula that I presented to you in the lecture. But it is an interesting and important one, so please do take a look into the lecture. This again is a question was asked during the quiz session by one of your colleagues. It's not a math problem, but I just want to re-emphasize what I told them in case you didn't actually attend that. This was about the difference between absolute and relative dematerialization. I'll give you the overview or the idea about this thing, and then you will easily grasp the example. The key thing here is that, let's say I'm telling you that I improved a technology, or I improved an application by significant improvement in the technology. Okay, I reduced its footprint, I reduced its impact. Does it mean that the overall impact caused by that technology on environment or other places, has it actually reduced? Just because I improve a unit impact by improvement in technology, it doesn't necessarily translate into overall absolute gains in reality. Do you see? Here's an example Professor Václav Smil produced in his book. He said that the Ford model in 1920, the American cars, had a relatively very low mass to power ratio. Okay, after 100 years, you could see that it improved from 15.3 gram per watt to 1 gram per watt, which is 94% reduction in less than a century. Significant gain. But has that actually translated into something absolute, something concrete? Professor Smil says no. Why? Because the model during 1920 had an average power rating of 15 kilowatt, whereas the vehicles that we have now has reached a peak of 171 kilowatt. You see, it's almost 12 times as powerful. Just because you improve the mass to power ratio, it doesn't mean much if you have a huge power rating at the end of the day. Okay. Also, in 2015, the average US vehicles were 3.6 times heavier than the ones that we were talking about in 1920. Okay, so these things actually erase the gains that we get from the technological advances. That is the difference between absolute dematerialization and relative dematerialization. Hope that was clear. Hope all the math related problems were clear. Please don't be afraid of math related problems. They are very simple plug and play. I'm not interested in actually, let's say, you doing the math to the last decimal or anything. My idea behind giving you math related problems is just to, let's say, get the substantiation part or the analytical part in your mind working, to understand or to grapple with the facts. Okay, that's all there is to it. Good luck with the exams.